Hello my friends and welcome back to the YouCanDo TV channel. Forging is one of humanity's oldest technologies. For thousands of years, hammers, driven by muscle, water, or heavy mechanical systems, have struck glowing metal with immense force. Traditionally, these blows were unrestrained, but a new generation of forging hammers is changing the rules. The linear die forging hammer combines precision with efficiency, delivering massive energy while maintaining extraordinary control. At Reed Schottler GmbH in Hagen, Germany, the linear hammer operates alongside a 19th-century double-belt hammer. While the old system strikes red-hot blanks at more than 1,000 degrees Celsius with a blow energy of 6 meter-tons, the new hammer can stop within 0.05 millimeters, producing highly accurate parts. Despite striking with the force of a 1-ton drop from 2 meters, it applies this energy only until the desired shape is achieved. This saves wear on the dies and reduces wasted energy. Unlike hydraulic hammers, which require constant pressure and costly oil maintenance, the linear hammer uses an electric linear drive. Coils and magnets are arranged around a steel cylinder, producing direct linear motion. A ram at the base holds the upper die, while the workpiece rests on the lower die. The result is precision forging with minimal scrap, around 25% energy savings, and up to 10% material efficiency gains. The advantages extend beyond cost savings. In automotive and heavy-duty applications, forged components must endure extreme forces. For example, connecting rods exposed to high rotational stresses must be dimensionally identical. The linear hammer eliminates the need for regrinding or calibration, cutting out entire finishing steps. It also allows precise production of truck safety parts, pump components, chemical fittings, and even titanium forgings. The accuracy of this system opens opportunities in new sectors such as aerospace, where flawless precision is mandatory. Meanwhile, in Oelsnitz, Saxony, Alger Sachsen GmbH demonstrates another breakthrough: cold sheet metal forming with the VarioTempo process. Instead of hot forming, automotive body panels are shaped at room temperature in powerful presses exerting up to 500 tons. Each blank passes through 7 consecutive forming stages inside the press. The key innovation lies in the third step, where a die presses the sheet at varying speeds, achieving exceptional draw depths of up to 280 millimeters without heating. This approach provides multiple advantages. Traditional cold forming of complex parts often requires splitting a component into 2 halves, welding them together, and using material overlaps, adding weight and waste. VarioTempo, by contrast, forms even highly complex geometries in a single integrated cycle, avoiding weld seams and reducing both material use and weight. In some cases, material consumption drops by 40%, while weight can be reduced by up to 60%, thanks to the use of high-strength steels. Currently, About 5% of Allgaier's production uses VarioTempo, but the share is set to grow. With over 1 million automotive parts produced annually, the technology offers a clear path toward more sustainable and lightweight vehicle manufacturing. Together, these two advances, the linear forging hammer and VarioTempo cold forming, highlight how even ancient metal shaping techniques can be reimagined for the 21st century. Both systems cut energy consumption, extend tool life, reduce material waste, and improve precision. They not only optimize existing processes but also enable entirely new applications. Forging and pressing may be centuries-old industrial arts, but as these innovations show, they still hold vast potential for efficiency, sustainability, and engineering breakthroughs. Sometimes, the oldest technologies deliver the newest surprises. Industrial springs are essential mechanical components designed to store, absorb, and release energy under load. They play a critical role in machinery, vehicles, energy systems, and precision devices, ensuring safety, efficiency, and reliable performance. Manufactured from high-grade alloy steels, stainless steels, or specialty materials, industrial springs are engineered to withstand heavy stresses, high temperatures, and corrosive environments. The production process begins with the careful selection of wire, rod, or strip material, which is then coiled or formed using advanced CNC coiling machines. Heat treatment follows to optimize mechanical properties such as hardness, resilience, and tensile strength. This step ensures the spring maintains dimensional stability and fatigue resistance during repeated compression, extension, or torsional cycles. Surface finishing techniques further enhance durability. Options include shot peening, which increases fatigue life, and coatings such as chrome plating, ceramic filled layers, nitriding, or PVD coatings that improve corrosion and wear resistance. In specialized applications, springs may also undergo stress relieving and precision grinding of the ends to ensure uniform load distribution. Industrial springs come in many forms: compression springs for heavy loads, extension springs for tension applications, torsion springs for rotational force, and disc springs for compact high-force requirements. Each type is designed to meet specific mechanical and operational needs. Quality control is vital, with every spring tested for dimensional accuracy, load characteristics, and compliance with international standards. The result is a versatile, high-performance component that supports industries from automotive and aerospace to energy, construction, and precision engineering. The Piston Rings division of Bühler UK specializes in the production of piston rings and sealing rings for combustion engines and hydraulic applications, complemented by castings and precision machined units. Annual output reaches approximately 25 million piston and sealing rings, alongside nearly 1 million cast and machined components. The foundry manufactures both ductile and gray iron using medium-frequency induction furnaces. 4 furnaces are currently in operation, 2 with 2-ton capacity and 2 with 1-ton capacity, melting raw iron together with recycled material. Cast blanks are then precisely machined into free shapes, ensuring dimensional accuracy and functional performance critical to engine efficiency and reliability. Surface treatment technologies represent a major field of advancement. Alongside standard hard chrome plating, the division applies modified chrome ceramics, which form microchannels filled with hard particles to enhance durability in modern engines. Additional treatments include molybdenum spraying, nitriding, and advanced PVD coatings, which deposit hard, thin layers on ring surfaces to further improve wear resistance. These treatments extend product life under extreme conditions. Development processes integrate rigorous engine testing of prototype piston rings, enabling validation of new materials and finishes. The technical archive comprises around 9,000 engineering drawings, covering 500–4,000 producible types. This broad portfolio supports manufacturing for diverse applications, ranging from small chainsaws and compressors to heavy-duty piston rings for trucks, tractors, generators, and specialized machinery. Continuous investment in precision machining, surface technologies, and foundry processes ensures the ability to meet evolving industry demands while enhancing durability, efficiency, and performance of piston rings across all applications. The production of green pin shackles is a carefully engineered process that combines advanced forging technology with strict quality control to ensure maximum strength and reliability. It begins with cutting high-grade steel bars, the raw material chosen for its durability and load-bearing performance. Next, the steel undergoes forging of the shackle eyes, where precise dies shape the ends that will later accommodate the pin. The bending of the shackle body follows, giving the steel its recognizable U-shape while maintaining structural integrity under heavy loads. Once the body is formed, controlled cooling stabilizes the metal's microstructure, enhancing toughness and fatigue resistance. In parallel, the shackle pin is forged to exact dimensions, ensuring smooth fitment and high shear strength. After machining and inspection, both body and pin are subjected to protective painting or galvanizing, safeguarding them from corrosion in demanding environments such as marine, offshore, and construction industries. Finally, the assembly stage integrates the pin with the shackle body, followed by rigorous proof load testing and certification. The result is a green pin shackle that meets international safety standards, delivering unmatched reliability in lifting and rigging operations. Aluminium is one of the most versatile and sustainable materials of modern industry. Known for its lightweight, strength, and corrosion resistance, it plays a vital role in transportation, construction, packaging, and energy sectors. From high-speed trains and aircraft to energy-efficient buildings and recyclable beverage cans, aluminium delivers performance while supporting a greener future. At the heart of this industry are aluminium plants, where cutting-edge technologies transform raw bauxite into finished products with precision and efficiency. Modern plants integrate advanced smelting, casting, rolling, and extrusion systems, ensuring consistent quality and high productivity. Digitalization, automation, and energy-efficient processes help reduce costs, lower emissions, and maximize resource utilization. Beyond technology, aluminium plants bring significant economic and social value. They create skilled jobs, strengthen regional economies, and contribute to circular production through recycling, where aluminium can be reused endlessly without losing properties. With global demand rising, aluminium plants are not only industrial hubs but also innovation centers, shaping lighter vehicles, smarter packaging, and sustainable infrastructure. In short, aluminium and its plants embody progress, efficiency, and value creation for industries and society alike. The aluminium cut-to-length line by Kohler is designed to deliver scratch-free decoiling and the highest leveling quality for demanding industrial applications. The process begins with the unwinding of large aluminium coils handled with precision to prevent surface damage. Advanced decoilers maintain consistent tension, ensuring smooth feeding into the leveling system. The leveling stage is critical, as the sheets must achieve perfect flatness without residual stresses. Kohler's high-performance levelers use multiple precision rollers to remove even the slightest distortions, guaranteeing sheets of uniform quality that meet tight tolerances. Once leveled, the material enters the cutting section, where a specially developed saw replaces conventional shear technology. This saw ensures burr-free edges, precise dimensions, and minimal thermal impact on the material. The cutting process is optimized for both thin and thick aluminium sheets, allowing flexible production across a wide range of specifications. After sawing, the finished sheets are discharged onto stacking systems designed to handle the material carefully and maintain its flawless surface. These sheets are then ready for downstream processes, including the welding of silos and other aluminium-based structures. With automation, advanced leveling technology, and a unique sawing solution, Kohler's cut-to-length line sets a benchmark for precision, productivity, and material protection in aluminium sheet production. VarioTempo, based near Aachen in the heart of Europe, is highly specialized in the production of pressed steel rims and complete wheel assemblies for industrial and agricultural applications. Every project starts in the engineering department, where advanced 3D CAD software is used to design rims according to customer specifications and ETRTO standards. Then raw steel, supplied in coils or flat sheets, which forms the foundation of every rim. This steel is first processed using a combination of laser cutting, 3D profiling, punching, and hydraulic deep drawing. These methods allow VarioTempo to shape the metal with high precision, ensuring each piece conforms to the strict dimensional requirements needed for rim performance. Once the initial blanks are prepared, the next stage is precision pressing. Using specialized dies, many of which are designed and produced internally by VarioTempo, the steel sheets are formed into the complex geometries of rim halves or complete rim structures. The advantage of having an in-house die-making facility is the ability to adapt quickly to customer-specific needs, guaranteeing flexibility in both small batch and large volume production. After pressing, machining operations such as CNC turning and milling refine the dimensions of the rims. This ensures that the final geometry is within micrometer tolerances, a critical factor for balancing, strength, and the long-term reliability of the wheels in heavy-duty use. The forming process is followed by assembly and joining techniques. Depending on the product type, rim parts may be welded together using circular welding or spot welding, or mechanically joined with hubs, discs, or bearing housings. This step transforms rim halves into complete wheel units ready to handle significant operational loads. After assembly, the rims enter the surface treatment line, which is one of the most important stages in ensuring durability. VarioTempo operates a modern powder coating facility that combines several phases: degreasing, phosphating, rinsing, powder spraying, and oven curing. This coating process produces a uniform, scratch-resistant finish that offers excellent protection against corrosion and harsh environments, particularly in the agricultural sector, where equipment often works in mud, moisture, and acidic conditions. Quality assurance runs parallel to production. Every rim undergoes dimensional inspection with 3D measuring systems, weld integrity checks, and coating adhesion tests. Compliance with international standards, particularly ETRTO guidelines, ensures that the rims are safe and fully compatible with the intended tires and applications. YouCan's ISO 9001 certified system reinforces this commitment to consistency and reliability. Once rims pass quality control, the final stage transforms them into ready-to-use wheels. Tires are mounted onto the rims using specialized hydraulic equipment that guarantees proper seating without damaging the coating or bead area. Inflation and balancing follow, ensuring the wheel is perfectly aligned for safe operation. Each finished assembly is then carefully packaged, often with protective wrapping or palletized storage, to prevent scratches or deformation during transport. Have you ever wondered how a simple piece of pure silver transforms into a shining coin, ready to be held in your hand? The journey begins in the furnace, where fine silver is melted at nearly 2,000 degrees Fahrenheit. At this point, the metal is alive with energy, glowing and ready to be shaped. Poured into molds, it becomes heavy billets, each the foundation of something extraordinary. From there, the billets enter a powerful extrusion press, sliding through dies to form perfectly uniform silver strips. Fans cool the strips, workers inspect every inch, and only the flawless pieces move forward. Then comes a magical moment. The blanking press punches out perfectly round discs. Each one is carefully measured to weigh exactly 1 troy ounce. No more, no less. Precision here is not optional, it's essential. But a silver blank is only the beginning. In tumbling machines filled with stainless steel beads, the discs are polished until they shine brilliantly. They're smoothed, cleaned, and prepared for their true identity. Skilled engravers design the dies, carving intricate patterns and timeless symbols into hardened steel. These designs capture history, artistry, and value in one powerful impression. Finally, under immense hydraulic pressure, the polished silver blanks are struck between engraved dies. In that instant, they are transformed, no longer simple metal, but coins carrying beauty, weight, and trust. Every step of this journey, from molten silver to the final strike, reflects craftsmanship, technology, and tradition. Silver coins are more than currency. They are pieces of art and heritage shaped by fire, steel, and human precision. The full automatic anchor bolt production line is a highly engineered system designed to integrate precision machining, automated handling, and efficient assembly into one continuous process. It begins at the CNC operating platform, where production parameters are programmed, allowing real-time control of all downstream operations. Raw material is introduced via the automatic feeding machine, ensuring consistent input without manual intervention. The material is then straightened in a 360 degrees raw material straightening machine, which eliminates bends and ensures uniformity, before entering the aggregate conveyor that transfers it smoothly to the cutting stage. Cutting is performed by a crocodile-type hydraulic cutting machine capable of high-strength shearing. Following this, numerically controlled sizing adjusts the workpieces to exact dimensions, and hydraulic bevel angle cutting provides accurate chamfers as required. The prepared stock enters the number 1 automatic production line, where a combined-type hydraulic necking machine shapes the bolt heads. Immediately afterward, the hydraulic thread rolling machine forms precise threads through cold deformation, guaranteeing strength and accuracy. For faceting integration, a nut screening machine ensures only quality-tested nuts are used. These proceed to the automatic screw machine of combined nuts, where damping nut bolts and non-planting types are processed directly into the next station. Further shaping is carried out by a full automatic punching and pin machine, adding essential locking features. The process concludes with strapping and finishing, where the bolts are cleaned, aligned, and secured with an automatic steel strapping machine before storage. A CNC stack crane then organizes the finished products efficiently in the warehouse. The system is further enhanced with advanced equipment for high-capacity lines. Additional stages include combined-type spinning and impact extrusion machines, which improve bolt head geometry, and cold rolling mills that refine the threads with even greater accuracy. Automated point welding and twist machines provide reinforcement and specialized configurations for custom anchor bolt designs. Each of these processes is seamlessly integrated, ensuring minimal downtime and maximum throughput. Quality is embedded throughout the production chain. The automated line reduces human error, while hydraulic forming and CNC controls deliver repeatable precision. Cold working methods enhance the metallurgical properties of the bolts, improving fatigue resistance and load capacity. Automated inspection systems, such as nut screening and dimensional controls, ensure that only bolts meeting international standards progress to the packaging stage. Finally, packaging is performed in line. The strapping and finishing machines prepare bundles of bolts, and the CNC stack crane handles palletization and organized storage. This fully automated workflow eliminates bottlenecks, increases production speed, and guarantees consistent, high-quality anchor bolts suitable for demanding construction and industrial applications. The creation of an aluminium ladder isn't just manufacturing, it's a choreograph of precision and automation. This fully automatic ladder production line transforms raw extrusions into sturdy, safety-compliant ladders with minimal human intervention. The process begins at the decoiler, which unwinds long aluminium profiles with meticulous tension control to avoid surface scratches. Next comes punching, where CNC-driven punches cut holes into the side rails at exact positions, critical for step alignment and compliance. Then, rung insertion takes over. Robotic arms align the steps and place them into the side rails. Moments after, the expanding process secures those steps through internal expansion, creating tight, durable joints without welding. This fully automated workflow eliminates bottlenecks, increases production speed, and guarantees consistent, high-quality anchor bolts, suitable for demanding construction and industrial applications. Next in line is flaring and orbital riveting. The rungs are flared or peened outward inside the rail, locking them securely and ensuring long-term stability under load. Every operation is merged into one seamless machine. The high-speed system can produce a meter of ladder every 20 seconds, efficient and consistent across folding ladders, platform ladders, multi-purpose ladders, and more. The line can also adjust rung spacing, typically 180 to 350 millimeters, and width, 220 to 650 millimeters, to suit diverse ladder types. Automation extends to error-proof controls. A central PLC system continuously monitors positioning, mechanical force, and cycle timing. If a misfeed occurs, the line halts instantly, protecting materials and preserving safety. Behind-the-scenes hydraulic power, rated around 16 megapascals, delivers the force needed for expansion and riveting, while pneumatic systems manage component handling and feeding at 2.5 to 4.0 bars. This production line is compact but powerful, measuring roughly 15 meters times 2.6 meters times 1.5 meters and weighing nearly 5 tons. It brings unmatched output speed and quality, with just one operator overseeing the run. The final result of AMI's production process is a step ladder that combines lightweight construction, ergonomic design, and reliable performance. Whether used by contractors on demanding job sites or by homeowners for everyday tasks, AMI step ladders embody safety, efficiency, and long-lasting quality. Once the ladder emerges, it rarely needs additional assembly or finishing. Each step is perfectly aligned and securely attached, ready for packaging or further finishing, like painting or PL coating. Quality is embedded throughout the production chain. The automated line reduces human error, while hydraulic forming and CNC controls deliver repeatable precision. Cold working methods enhance the metallurgical properties of the bolts, improving fatigue resistance and load capacity. Automated inspection systems, such as nut screening and dimensional controls, ensure that only bolts meeting international standards progress to the packaging stage. The CBM-12 chain machine by OHA Group is a specialized wire machinery designed for producing strong and reliable metal chains with minimal human intervention. It handles wire diameters ranging from 6 to 12 millimeters, enabling the creation of thicker and more durable chain links suitable for demanding applications. The machine produces approximately 14 to 21 links per minute, striking an ideal balance between production speed and high mechanical integrity. Equipped with an automatic feeding and forming mechanism, the CBM12 ensures consistent shaping and linking of wire, while its interchangeable molds provide flexibility in manufacturing different chain patterns and sizes. This adaptability makes it valuable for industries requiring heavy-duty chains in machinery, construction, transportation, and industrial hardware. By combining precision wire handling with robust forming technology, the CBM12 offers an efficient, versatile, and high-quality solution for modern wire machinery applications. The Bühler extruder is designed to deliver precision, flexibility, and reliability in modern production environments. Its operation can be divided into several well-coordinated sequences that demonstrate both the engineering sophistication of the machine and the efficiency it brings to industrial applications. The process begins with the assembling of the screws, a critical step to configure the extruder according to product specifications. Different screw elements can be combined to adapt shear, mixing, and conveying capabilities, ensuring optimal processing of raw materials. Once assembled, the startup phase is initiated, where temperature control systems, feeders, and lubrication units are activated to bring the machine to stable operating conditions. When production begins, raw materials are fed into the extruder barrel and undergo precisely controlled thermal and mechanical treatment. The screw configuration ensures consistent mixing, melting, and homogenization, resulting in a uniform output. Throughout the run, integrated monitoring systems track torque, pressure, temperature, and throughput, allowing operators to maintain product quality. For safety, the extruder includes an emergency stop function, which instantly halts all motion while protecting both the machine and operators. Equally innovative is the automatic screw push-out system, which enables quick disassembly and cleaning, reducing downtime between production runs. When a recipe change is required, operators can rapidly switch processing parameters via the digital control interface. Adjustments to screw speed, temperature zones, and feeding rates ensure seamless transitions between product types with minimal waste. At the end of a cycle, the shutdown procedure cools the system in a controlled manner, safeguarding the mechanical components and preparing the extruder for maintenance or the next run. The Bühler extruder thus exemplifies state-of-the-art extrusion technology, combining flexibility in screw design, efficiency in operation, and robustness in safety features. Whether for food processing, feed production, or advanced material applications, the machine delivers consistent performance, fast changeovers, and optimized productivity. Every great engine begins with a hidden masterpiece, the turbine blade. Born from fire, precision, and centuries-old craftsmanship refined by modern science, Each blade is more than metal. It's a marvel of engineering. At Safran, its journey from digital design to finished part reveals a story of innovation and resilience. The birth of a turbine blade at Safran begins in the design office, where engineers transform aerodynamic, thermal, and mechanical requirements into a precise 3D CAD model. Using advanced CAE simulation tools, they subject the design to digital stress, heat flow, and fatigue analyses to predict performance under extreme engine conditions. These simulations ensure the blade will withstand thousands of cycles at high rotational speeds before the first prototype is even manufactured. Once validated, the model is transferred to the process engineering team, who adapt it for industrial feasibility and design the molds and cluster structures required for lost wax casting. The lost wax process starts with wax injection into steel dies, forming exact replicas of the blade. Fragile ceramic cores are inserted to create internal cooling channels. Each wax model is ultrasonically inspected to confirm core alignment. Clusters of wax blades are then repeatedly dipped in ceramic slurry and coated with fine and coarse sand. Between each of the 7 to 9 layers, controlled drying times ensure adhesion and shell integrity. This meticulous multi-layer process produces a shell strong enough to endure molten metal at more than 500 degrees Celsius. The wax is removed in autoclaves under pressure to prevent cracking, and the empty shells are further baked to harden and remove residual wax. Casting involves preheating the ceramic shells before molten superalloy is poured. To achieve the required microstructure, directional solidification and controlled cooling rings are used, improving creep resistance and fatigue strength. Once cooled, shells are broken away, cores dissolved in chemical baths, and the rough blades separated. At this stage, the components undergo heat treatment cycles that enhance grain uniformity and optimize thermomechanical properties. Protective coatings, such as aluminides or ceramic thermal barrier layers, are later applied to resist oxidation and extreme temperatures. Inspection and dimensional validation are crucial. Each blade is subjected to non-destructive tests, including X-ray radiography, ultrasonic analysis, and penetrant testing to detect internal or surface flaws. Three-dimensional coordinate measuring machines record over 150 points per blade, ensuring geometric accuracy within microns. Airflow tests verify that cooling holes drilled by precision EDM micro-drilling meet design specifications. Every blade is fully traceable by heat number, serial marking, and digital records, ensuring accountability from melt to finished product. Final finishing includes grinding, rectification, and edge rounding to improve aerodynamic efficiency. Additional parts such as wear-resistant stellite tips are brazed on, and the entire component is subjected to final coating treatments. After serialization, weighing, and packaging, the blade is documented with photographs of its box placement to guarantee traceability through assembly. The result is a turbine blade that embodies the synergy of digital design, advanced materials, and rigorous quality assurance. From simulation to casting, from ceramic shell building to high-precision 3D measurement, every step ensures that the component meets the highest standards of reliability. This combination of engineering excellence and meticulous craftsmanship allows Safran to deliver blades capable of operating in the harshest environments of modern aero engines. Seiko's Turbo 10 high-feed helical milling cutter delivers exceptional performance in demanding contouring and profiling applications, offering high feed rates, substantial depths of cut, and superior metal removal efficiency. It outperforms conventional square shoulder mills by enabling significantly deeper cuts and improved tool engagement. The cutter body features high-precision, robust insert pockets that ensure axial stability and minimize insert-level mismatch for consistent surface quality. Inserts compatible with the Turbo 10, such as XOX10 T3 variants, provide low cutting forces and clean 90 degrees wall capabilities when properly aligned, reducing secondary operations. Available in tooling systems including CombiMaster, Weldon, Arbor, and Seiko Weldon, Turbo 10 delivers flexibility for slotting, pocketing, ramping, and helical milling with enhanced precision and tool life. HIN. The dough-feed high-feed milling cutter is engineered for productivity and cost efficiency, featuring double-sided inserts that provide 6 cutting edges, up to 3 times more than conventional designs. This reduces insert costs, especially when machining stainless steels and hard-to-cut materials where wear is accelerated. A robust cutting edge with an obtuse angle prevents fracture, while a wide contact face ensures secure insert seating and operational stability. The cutter also excels in ramping applications, with longer inner cutting edges enabling higher ramp-down rates, increased ramping angles, and enhanced performance in both linear and helical milling operations. Newburgh Heavy Fabrication Division, HFD, operates a 115,000 SQM facility in Gujarat, India, specializing in the production of heavy process equipment such as pressure vessels, heat exchangers, columns, absorbers, and storage tanks. The manufacturing process begins with precise design drawings and digital simulations. High-grade steel plates are cut, rolled, and formed into shells and sections, followed by advanced automated welding under strict quality procedures. Heat treatment ensures proper mechanical properties, while non-destructive testing verifies structural integrity. Each unit undergoes hydrostatic and dimensional testing before painting, assembly, and packaging. Certified to ASME standards and delivers durable equipment for chemical, petrochemical, oil and gas, and energy industries worldwide. The water tank rotomolding machine is specifically designed for producing durable rainwater collection tanks through a precise rotational molding process. The cycle begins with loading a pre-measured quantity of polyethylene powder into the mold. The closed mold is then placed inside the oven, where it is uniformly heated while rotating biaxially. This simultaneous heating and rotation ensures the polymer melts evenly and coats the entire inner surface of the mold, achieving consistent wall thickness without weld lines. Once the heating phase is complete, the mold is transferred to the cooling station, where controlled air and water cooling solidify the molten material without causing deformation. The mold is then opened, and the finished tank is carefully removed. Tanks produced with this method exhibit high structural integrity, seamless construction, and resistance to impact, corrosion, and environmental stress cracking. Rotomolding technology enables flexible design, allowing various capacities and geometries to meet different rainwater harvesting requirements. When round metal stock enters a rolling mill factory, it first passes through a straight finishing mill, where primary reductions and dimensional corrections occur. Once the material achieves the required base dimensions, it proceeds to the block mill, also known as a finishing block mill. Block mills are engineered for high-speed, high-precision rolling, typically used for transforming intermediate bar or wire stock into final dimensions. These mills often employ a top-crossed 45 degrees configuration, minimizing twist contamination and providing a stable rolling process across multiple stands. As stock moves into the block mill, it undergoes continuous microtension rolling across several stands, often from 10 and wire rod lines. The result is a tightly controlled and finely finished product with excellent dimensional accuracy. Typical entry materials range from 17 to 21 millimeters, while the output can be as small as 5.5 to 16 millimeters wire rod or rebar. These finishing block mills operate at exceptionally high speeds, often exceeding 90 meters per second and sometimes approaching 110 to 135 meters per second, depending on material and model. Their design, including features like tungsten carbide rolls, cantilever shafts, and durable bevel gearboxes, reduces maintenance and enhances both stability and output quality. An advanced alternative, the reducing and sizing mill, RSM, is positioned downstream of the block mill but before final finishing stages. It's built for flexibility and lower energy consumption. With its twin module structure, RSM allows for partial bypass during maintenance and supports high-quality rolling with reduced downtime. Together, the straight mill, block mill, and optional reducing/sizing mill create a highly efficient hot rolling sequence. Initial shaping occurs in the straight mill, while the block mill delivers fast, twist-free, and dimensionally accurate rolling. For additional refinement and operational flexibility, the RSM can offer precise sizing while balancing energy use and maintenance needs. The SBR3 spiral blade cold rolling mill machine, also known as a screw flight making machine, is an advanced continuous forming system designed for the efficient production of spiral blades. This machine operates on the principle of cold rolling, where a pair of specially designed tapered rollers gradually thins the edges of a flat steel strip. Through this controlled process, internal stress is introduced into the material, causing the strip to curve naturally into a precise spiral shape without the need for additional heating. Powered by two high-torque 11 kilowatts motors, the SBR3 delivers strong and stable forming capability, making it suitable for processing both mild steel MS and stainless steel SS. The machine can handle strips up to 6 millimeters in thickness, allowing for the manufacture of robust and durable screw flights. Spiral diameter and pitch can be flexibly adjusted according to specific design requirements, ensuring versatility across different applications. The screw flights produced are primarily used in conveyor machines, where they serve as the driving component for material transport in industries such as mining, agriculture, and construction. With its high efficiency, precision forming ability, and reliable performance, the SBR3 spiral blade cold rolling machine provides manufacturers with a cost-effective solution for large-scale production of spiral blades.